Last time we've rendered this scene, which includes two kinds of materials, diffuse and basic ones. Well, today is time to take reflections to the next level. In a nutshell, diffuse materials reflect light while basic ones don't. However, in real life, every object must emit some kind of light. After all, you'll never see pure red objects in real life, with exception making the light sources, of course. In this video we'll mainly focus on that, but first let's perfect the diffuse materials. Although this scene looks pretty decent, it has a couple problems. The first thing that hurts my eyes might be the noise. This effect is caused by the way diffuse materials reflect light, which is basically random. Let's visualize it. Suppose that some ray hits a sphere in point P1, then another one hits the sphere in point P2. Although the two intersections are really close to each other, they determine different hues. This causes those sudden changes in colors. A logical approach to remove noise might mean each time a ray hits a diffuse sphere, casting multiple random rays instead of one and merging their colors. Now, the sphere basically doesn't emit the color of surrounding materials, but rather that of the entire environment. Unfortunately, this approach might be computationally too expensive and also pretty hard to implement in code. You can still use it, but there is a better solution. We can go around in a similar fashion by generating multiple rays per pixel. How does this work? Currently we cast a single ray for each pixel. Again, nothing stops you from shooting more than one ray per pixel. You can send however many you want in random directions and simply merge their color. The following code averages their hue using an arithmetic mean. But be careful about how random those directions are, because you might accidentally blind your ray tracer. Scale the randomness down a bit. This also causes an anti-aliasing effect, which basically removes the other sudden changes in your scene. Now your code might be 10 times slower depending on how many rays you cast, but I think it's worth the sacrifice. As I mentioned in the beginning, diffuse materials aren't the only ones to reflect light. In fact, any surface does this, but in a different way. You might have heard about specular reflections before. They reflect light in this perfect mirror-like manner, which result into those crystal clear reflections. How do they work? We want to cast the ray symmetrical with respect to the normal. Consider this formula, which takes the incoming light direction and the surface normal, and returns the reflected light direction as an output. This formula works by projecting the initial ray onto the normal. Let's use it inside the code. Note that we need to change the way we're handling color, since now we manage reflections differently. So let's return the reflected ray's color multiplied by the info material's color. This modification allows diffuse materials to have different hues and handles the specular one's color effectively. Let's talk about why we actually multiply their color instead of adding it or something. At the moment we are using RGB to handle colors, which defines them by 3 numbers. You might have heard before that in real life specific materials absorb part of the light's color. Consider a ray that hits a red sphere, the sphere's color being 0.9, 0.2, 0.2. Suppose the initial color is 1. Multiplying it by a fractional number should scale it down. Most of the remaining color is in the ray channel, since that's the one mainly not absorbed by the object. Let's say then a ray hits a blue sphere and we multiply the color by 0.2, 0.2, 0.9. The final result is a pretty dark color formed by merging those two colors. That is a pretty accurate representation of how light travels. Let's finally run the code and... Did I make a mistake? Oh yeah, it seems the background being 0 basically absorbs all the light, so let me set it to 0.7. If you take a closer look at these reflections, they look suspiciously perfect. To make them blurrier, let's offset them by some random unit vector. That's a bit too much. so we can scale it by some scalar, which we'll name fuzziness and consider it a material property. We'll also update the diffuse materials just to have a bit more control over them. And as a fun fact, now you can set the sphere's color to something really bright, like 1000. It will act just like a light source in the scene. We can make this scene better by adding a floor. How do we do that? If you think about it, we can check the intersection with the plane situated at y0 pretty easily. Consider a ray. If its origin y is positive and the direction y is negative, then that specific ray will logically hit the floor at some point. The same goes for a ray which origin y is negative and direction y is positive. We can translate this to a ray hits the floor if the origins y times directions y is less than 0, because if their product is negative, then they have different signs. If a ray hits the floor and misses every sphere, let's return a different color. We can continue by finding the actual intersection point, which is a very easy task. As you all already know, any point on a ray is described as ray origin plus redirection times t. Since you only care about y for this plane, think about it as 0 is equal to ray origins y plus redirections y times t. Now just obtain t from this equation and use it to find a point on the ray. It might help rewatching parts 1 ray description in order to understand those steps better. At the moment we know where a ray intersects this plane. To draw that texture you saw in the beginning of the video, you can simply draw pixels if their sum between the points x and z components is an even number. Let's code this. First, get rid of the intersections y component. Then round piece components, and if their sum is an even number, return a dark pixel. To scale the grid, you can divide the points x and z components by anything just before you round them. We can continue by adding even more objects into our scene and mess around with more complicated concepts, but I believe this is an appropriate end for this video. As always, if you have any suggestions, questions or anything else, comment them. See you next time.